Welcome. This is Mrs. Nearing, and in this video, we're going to be talking through the first parts of both the 2006 and the 2009 FRQs that were related to Unit 1. So these are ones I posted in there for the Unit 1 review FRQs. And if you look at this 2006 one, it looks like a combustion analysis question. Oops. Combustion analysis. And if you have not already done so, I recommend you pause the video and go through and try this problem on your own first. This video is going to be much more helpful if you've taken the time to think through this question yourself and give it a try and see where you're getting stuck. And then you can come back and check your work here. And do make sure you check your work, even if you're confident you got the right answer, come back and check it. Okay, so some things we know here is we know that we have a compound containing these elements. So they contain C, H, N, and O. And we know the mass of the compound is 1.2359 grams. So that's the mass of this entire compound. Okay. And when we burn it in the presence of oxygen, we make some CO2 and water. They don't tell us anything about the water, but they do tell us that we make 2.241 grams of CO2. And another piece of the combustion analysis showed us that we make 0.0648 grams of hydrogen. So those are the things that we know. So it's combustion analysis, but maybe a little bit different from what we're used to. So we're going to see what we can do with this information to answer the questions that we have here. So this first thing is we're going to determine the mass in carbon in the original sample. So we know in this sample that it contains these four elements. We don't know anything about the ratio of those four elements. So this number isn't going to be very useful for us to use to determine grams of carbon because we don't know what the composition of this substance is. So let's look for something that has a known composition, and that would be CO2. So we know that we have 2.241 grams of CO2, and we should be able to convert grams of CO2 to grams of carbon. And then the nice thing about that is the way combustion analysis works and why this is a useful strategy is that all of the carbon in our CO2 came from this original sample over here. So if we can figure out how many grams of carbon were in the carbon dioxide that we collected, we will know how many grams of carbon were in our original sample. And there's two ways that I can think of approaching this. One is that you can use mass percent of carbon. So you can calculate what's the mass percent of carbon in CO2 and take that percentage of this number right here. So that's one method. The other strategy that you could use is you could do, a gram to mole to gram conversion. So let me show it that way, because in part 2 we'll look at a mass percent example anyways. So we're trying to get from grams of CO2 to grams of carbon. So first we convert grams of CO2 to moles of CO2. So 1 mole of CO2 is 44.01 grams. And then every 1 molecule of CO2 contains 1 atom of carbon. And then we know that a mole of carbon atoms weighs 12.01 grams. So we end up with 0.6116 grams of carbon. So that's the answer to I. How much carbon was in the original sample? So that's, so that's how much carbon was in my CO2, which is the same as the carbon in my original sample there. So that's I. Let's look at double I. Double I, they give us a mass percent. So we have, our original sample is 1.2359 grams, and it tells us that 28.84% of it is nitrogen by mass. So we could use that. We can convert this percentage here. Oops, sorry, I'm getting too close to the bottom of my screen here. Turn this percentage into a decimal, so that becomes 0.2884. Sorry, that looks like 2,000% here. Okay, and then 28% of 1.2359 is 0.3564. Notice my answers have 4 sig figs in them. So now we know the grams of carbon in our sample. We also know the grams of nitrogen. And remember, they told us the grams of hydrogen, so it looks like we're creeping towards being able to determine a chemical formula here. So let's look at the next part of this question. The next part is determine the mass in grams of oxygen in the original sample. And one thing I want to caution you against is it might be tempting for some of you to say, oh, I can find oxygen using the CO2 number, right? Just like I did for the carbon. The problem with this is that your oxygen actually has more than one source. So there's oxygen in your original sample, in your hydrocarbon, but there's also oxygen in the air. So the oxygen, the CO2, and the water are coming from several sources. So we can't use this number right here. We can't use that 2.241 number to figure out how many grams of oxygen were in our sample. What we need to do is just use some subtraction. So if you think about what we know so far, let's summarize it over here. We know that we have a sample that weighs 1.2359 grams. And that sample contains the elements carbon, hydrogen, nitrogen, and oxygen. We know that it tells us in the problem that what 0.0648 grams of that sample is hydrogen. And we calculated in I that 0.6116 grams of it was carbon. And then we calculated in double I that 0.3564 grams of that was nitrogen. So the way that we find the mass of oxygen is just by subtracting. So notice how we subtracted the hydrogen, subtracted the carbon, nitrogen. What's left is going to be grams of oxygen. And when we do that subtraction, you should get 0.2031 grams of oxygen. So that's the answer to triple I. And then for Roman numeral 4 here, it says determine the empirical formula. So the empirical formula is just a mole ratio. And you might remember our kind of steps there of our rhyme: percent to mass, mass to mole, divide by small, multiply till whole. So what we have right now are masses of my 4 elements. So we know the mass of hydrogen, we know the mass of carbon, we know the mass of nitrogen, and we know the mass of oxygen. So next step is we're going to go from mass to mole. So we're going to divide each of these by their molar masses. And that's, 14.0 divided by, I think it's 14.01, I think, 16.0. I want to keep a decent number of sig figs when I'm doing this type of calculation. I don't want to stop and round too early. Like for example, if I rounded 0.0648 to 0.06, that's going to be a pretty significant rounding happening there, which is just going to compound itself later on in the problem. So you want to keep at least, 3 sig figs maybe in this calculation as you're working through it. So you find the moles of all of them. So you end up with 0.06429 moles of hydrogen, 0.05092 moles of carbon. We have 0.02544 moles of nitrogen, and then this one is a lot of calculations here: 1269 moles of oxygen. I will say on the 2020 AP exam, they've said that the numbers will be simpler, that you will be asked to do calculations, but they're ones you should be able to do without a calculator. So the numbers will definitely be simpler than these ones, but you could still imagine doing some calculations. You can still do this type of calculation just with easier numbers. Like for example, instead of saying 0.6116 grams of carbon, they might just say 0.6 grams of carbon, divided by 12, and that's going to be an easier number, like a nice round number to work with. So they'll just use kind of simpler, cleaner looking numbers that you can deal with without a calculator if you had to. But of course, if you've got a calculator at home, use it. Okay, you're allowed to use it. So we did percent to mass, mass to mole, divide by small. So I'm going to look at these mole values and say, okay, which one is the smallest number of moles? It looks like oxygen is the smallest. So I'm going to divide everything by 0.01269, 0.01269. And that's going to give us a much cleaner, looking ratio. So what that tells us is for every 1 mole of oxygen, we're going to end up with, and make sure I label these correctly, I think this ends up being 5 moles of hydrogen and 4 moles of carbon and 2 moles of nitrogen. And so the way we might write that is C4H5N2O. And some people have asked in the past, what's the rule? Like, which element do you write first? And I'd say, first of all, for the AP exam, it doesn't really matter. Like, if you wrote N2H5C4O, they're still going to mark that correct because the purpose of this question is to figure out if you can determine the mole ratio. So they're not really going to care which order you write it in. The convention with hydrocarbons, though, is typically you write the carbon first and then the hydrogen. And then with other elements, you tend to write them in order of increasing electronegativity. So basically you go from left to right on the periodic table. It's kind of a good rule of thumb. Like that's why we write, we write sodium chloride, not chlorine, sodium. So, but it doesn't really matter. You're not going to get marked wrong if you put them in a different order, if you were wondering that. So let's take a look at one more question here. This is the 2009 FRQ. And we'll look at this one. Again, if you haven't tried it, pause the video and try it first, and then come back and we'll talk about it. Okay, so what we have here is we have a flask. So imagine maybe like an Erlenmeyer flask containing air. They flushed it out with an unknown gas, sealed it, and measured the mass. And we know some things about it. We know the temperature is at 23 degrees Celsius. We can convert that into Kelvin because that's sometimes useful. So that's 296 Kelvin. Remember that conversion is on your equation sheet. And we know that the pressure is 750 torr. And the way to interpret that decimal there at the end, that decimal makes this trailing zero significant. So this number now has 3 sig figs in it. So that's what that kind of final decimal does. If you're wondering why they put that there, is that a typo? No, it's intentional. Okay. So first you want to calculate the mass in grams of dry air that's in the sealed flask. So if we think about some things that we know that the density of the air is 1.18 grams per liter. So they gave us density and we're trying to find grams. So this kind of looks like a one-step calculation. If we can just take this value times liters, we'll end up with grams. So that's all we have to do for this one. It's really just a density calculation. So my volume of my flask is 843 milliliters. So I'm going to convert that into liters. And that's one thing that's not on your equation sheet is those metric conversions. So if that's something that you tend to make mistakes on, that would be a good thing to add to your note sheet, was conversions like, 1,000 milliliters is a liter. So think about what things you would find helpful to include in your notes. And when we do this, we're ended up with grams, and it looks like our answer is going to have 3 sig figs in it. So 0.995 grams is our answer. And again, sig figs, if that's something that tends to stress you out or you feel like you make a lot of mistakes on, make some notes about sig figs. Include that in your Unit 1 notes, that make you feel more confident going into this. So jot some notes down to yourself. Okay, so calculate the mass of the flask itself with no air in it. So that's an interesting question. Let's think about what we know. Well, we know the mass of the flask with the dry air is 157.7. So that's flask plus air. And then we know that the mass of the air is 0.995. So if we subtract those two values, we will get the mass of the flask alone. And noticing with sig figs here, our final answer can only go out to the hundredths place because the rule with subtraction is you're limited by, I always find it hard to phrase this one, you're limited to how many digits you can go to the right of the decimal. So this number goes 2 spots to the right of the decimal point. This number goes 3 spots to the right. So your answer can only go 2 spots to the right of the decimal. So you're going with the number that goes the fewest spots to the right of the decimal. I feel like I said that very awkwardly, but you know, this one goes the hundredths place, this one goes the thousandths place, so your answer can only go to the hundredths place. That's the rule there. Okay, and if you look at C, calculate the mass of unknown gas that was added to the flask here. So we know that if you look up here at this data table, 158.08, this is the flask and the unknown gas. Because we initially had, dry air. That's what, A and B are involving. Now we're putting some unknown gas there into your flask. And then we're going to subtract the mass of the flask alone. And that will give us the mass of the unknown gas, 1.37 grams. So that's our unknown. This value has 3 sig figs in it. So now let's go ahead and, I'm running out of room here, calculate the molar mass of the unknown gas. I might erase this stuff over to the side, and I'll do D over here. So if we think about what we know, and I'll use a different color of pen. Okay, so we're trying to find the molar mass, and the molar mass is the grams divided by moles. So we know what grams is. We just calculated that. It's 1.37 grams. That's what we figured out in part C. So now we have to figure out how many moles we have. And often we will find moles by using the molar mass, right? But we don't know the molar mass, so we can't use molar mass to find moles because that's the whole thing we're trying to find. But since we are dealing with a gas, remember there's another way in which you can find moles. You can use PV equals nRT, so your ideal gas law. So I can rearrange this and solve for N. So N equals PV over RT. And if you look at your pressure is 750 torr. Your volume, actually I'm going to skip ahead and look at R real quick. Once you've seen what units your pressure are in, look at your equation sheet and decide which R value makes sense to use. So in this case, I should be using the 62.36 value of R, because if you look at the units there, it's going to be in liters torr divided by Kelvin mole. Okay, so be really careful with units on this type of calculation. So notice since the R value has liters in it, I need to convert my volume from milliliters into liters. So I'm going to convert my 843 into 0.843 liters. So now my liters cancel out. And then notice how Kelvin is my other unit there. So that means my temperature needs to be in Kelvin. So it's going to be 23 plus 273, so that's, 296 Kelvin. So now when I stop and solve, I will end up with an answer that has units of moles. So my moles are 0.0342. And then what I'm trying to find is molar mass, which is grams divided by moles. So the molar mass is 1.37 grams divided by 0.0342 moles, and that will give me 40.1 grams per mole, and this will still have 3 sig figs in it. So this idea of finding the molar mass is something that could pop up in a situation like this with a gas. So we did a lab where we found the molar mass of a gas. We did slightly different steps here, but we had the same kind of idea. We measured mass of a gas, and then we figured out moles using ideal gas law and found the molar mass of a gas. You might also find molar mass of something using titration as a technique, so it's something that can pop up in Unit 4 stoichiometry applications. So it's definitely something that can pop up in different scenarios. And you will also notice some other things you might be asked to do percent error. And if you check your equation sheet, percent error, I don't believe is on there. So it's basically how far off you were divided by the original value there. So percent error would be, let's see, what we got for the molar mass. So let's call this the experimental value. That's what we calculated in the lab, was the, what was it? Was it 40.1? Okay, so our experimental value was 40.1 grams per mole. And they tell us that the, true value, or we'll call this, the theoretical value, was 44.0. So what you do to find the percent error is you're basically saying, how far off was I from the original? And this is an absolute value, so it doesn't really matter which way you subtracted it. And divide that by what the true value should be. So you're going to turn that into like a percentage here. So when you do that in this case, you should find that your percent error is 8.9%. So this is something you could theoretically be asked about. So this could be useful to include in your notes. Percent error is different from percent yield, so it could be helpful to define, those two different things. Percent yield, what is that? You can look that up. And also notice that there are some, experimental error analysis happening here. So if we, so this one you're just justifying your answer. So in this first one, the flask was incompletely flushed with CO2, resulting in some dry air remaining in the flask. And we're trying to decide whether these sources of error could explain, excuse me, what we noticed. And it's important for us to notice that our experimentally determined mass was too low. So our error gave us a mass that was too low, right? 40 grams per mole is smaller than 44. So you want to say, does this error fit with getting a mass that's too low? So this one could be responsible. Occurrence number one could be responsible because the dry air left in the flask could be less dense than CO2. So that would result in a lower mass of gas and a lower molar mass finding. And then occurrence two is, what if the temperature of the CO2 was lower? That occurrence could not have been responsible because the density of a gas is greater at a lower temperature. So then you would have ended up with a higher mass of gas in there and gotten a higher calculated molar mass. And I've got the answer keys, these ones posted in OneNote as well if you want to read through the scoring guidelines for F and G, because I don't want to write those all out right now. That would take too long. Okay, so feel free to look back at those ones. So hopefully this helped. Thanks for watching.